Alright, hell yeah. So we have statics, and this is Hibbler. And we have this kind of cool problem. So here is the example and the solution. So I'm going to just leave it there, and then flip to the next page, show you that. Okay, but we're going to get into, we're going to do something unique. In the last video, I used the dot product. We have a force of 2 kilonewtons. We want to know its moment arm, you know what I mean? Maybe this tree just requires a certain force times distance or certain torque about its root ball to actually topple this tree over. You know what I mean? We're just pulling kind of at a crappy angle, but you can't get you can't get this tractor on top of a cliff and then pull at a perpendicular. That would be the best. All right, so we want to know the moment, and so we did with the dot product. It's kind of unusual, but find this distance. The dot product in general kind of gives you this distance, but we knew with Pythagorean's theorem, we knew this height was 12. That's our hypotenuse, and we could easily get that. So now we're going to do that same process using the cross product. What we're not going to do is take the cross product of this distance crossed with this vector in the direction of this force vector. We're not going to do that. We're going to try to do it from a magnitude only perspective. So we're going to use the cross product, but try to just focus on what the cross product tells us about the magnitude. And so we are going to go to straight unit vectors. And I'm going to start, since these two vectors start at this point, I'm going to start here. And so I have a vector A to O. So that's going to be negative 12 in the k-hat direction. And so I'm going to make that a unit vector. It only has one component. So I'm going to say the unit vector. And so how would I write this? I think I will do, I like this term. So we have the unit vector from A to O is going to be negative 1 k-hat. Cool. And so now we want to find the unit vector of A to B. So let's do that. So we have the unit vector A to B. Well, it's just going to be how to get from A to B. We're going to go over 4 in the positive I direction. So we got 4I. Even just right now, though, we could, well, let's do it all in one go. But we are going to, well, now let's do it right now. So to get the unit component of this, we have to divide it by the magnitude of this whole distance. So I mean, we would go over 4, over 12, and then down 12. That was the other 3 components. But each of these components, we got to divide by this whole distance. What's that? It's like Pythagorean's theorem, but with 3, it's a little bit on steroids, but it still works. It's kind of fascinating. You can do the proof yourself just by saying, like, oh, this has a shadow component here. You know what I mean? So then you're just back to Pythagorean's theorem. This is totally a 90, and you have one side squared, and then the square root of that. You just do Pythagorean's theorem twice. No one does that, though, because you would have 12 and 4 to find this. You could easily find this, right? But then you're going to use that as this. It is good to go over the proof. You know what I mean? Well, and I'm not even going over the proof. I'm just going to say, hey, it's an easy one to remember just because it's this component. It's all the components squared. So 4 squared plus 12 squared plus negative 12 squared is 12 squared. Cool. All right. So, and that's going to be the unit component in the I direction. And now moving on, we have the J component. That's going to be 12J. And I'm just going to say, hey, just divided by all that stuff again. Cool. And then I'm going to have, to get from here to B, we got to go down negative 12. So we're going to go negative 12 in the K direction, divided by all that stuff. But we are going to throw this into our calculator just to do the double check. So I'm going to get this term first, just because we're going to have to use it 3 times. So 4 squared plus 12 squared plus 12 squared. I think it's like square root 309. Square root 309? Hell yeah. I don't know. But anyway, so we're going to store that in my calculator, and then, so I'm going to do 4 divided by that. So I stored this value as x in my calculator. So 4 divided by x. And what I like to do is store this as alpha I. Might as well, it's the I component. Cool. And then I'm going to do 12 divided by this magnitude, store that as alpha j. And then I'm going to do negative 12 divided by that, stored as alpha k. Sweet. So now here's alpha I, alpha j, alpha k. So we have 0.22, I'm just going to round it to 3, 0.228i plus 0.683j minus 0.683k. So this is the unit vector from A to B. And to do the double check is we're going to square each of these terms, you know what I mean? So if we take, what's the magnitude, you would write it like this. The magnitude of that vector is the square root, each of those components squared, you know what I mean? So that's kind of how I write it quick, just because it's a pain in the butt to write it all out again. So we're going to do the square root of alpha I squared plus alpha j squared plus alpha k squared. And if you have this in your calculator, it's just really easy to do a little double check. So I don't know why we're not crispy. So that's interesting. Let's try one more time. So I'm going to have the, yeah, that's interesting. Let's do 4 divided by the square root of 4 squared plus 12 squared. I don't know why I'm wasting my time on this, but yeah, we just didn't get 1. So I definitely just want to do a little double check. So I'm going to store this as alpha I. Whoa, whoa, whoa. Ah, bummer. Alright, so I'm going to store this as alpha I, and then I'm going to go 12. And then store that as alpha j. Then I'm going to go negative that answer, store that as alpha k. Sweet. So now I'm going to pull that square root. I squared plus j squared plus k squared. Whoa, what happens? Wait, what up? What up? So what did we do wrong? So we have 4, what up? Yeah, we have 4 divided by 4 squared plus 12 squared plus 12 squared. That's alpha I, and then we're going to do 12, and then we're going to store that as alpha j. Cool, and then we're going to do the negative of that stored as alpha k. Heck yeah, so alpha I squared plus alpha j squared plus alpha k squared. Alright, hell yeah. And then the square root of that. Square root of alpha I squared plus alpha j squared plus alpha k squared. Okay, holy Toledo. So we got them. And then what was alpha I, alpha j, alpha k? So we were 0.22. Yeah, I don't know where my calculator was messing up. There it was, 0.688. So we messed up somewhere. Alright, so we got back on track, so that's good. That was a bummer. Alright, but now what are we going to do with these? Okay, so what we have is now a unit vector. So let's just draw it in. It has a magnitude of 1. We also have this vector. It also has a magnitude of 1. So let's blow that up. So we have straight down. We have a vector of 1. And then at this angle, about a 45 degree, we have a vector. I kind of drew it too big. Yeah, close enough though. Alright, so we have a vector of 1. Now, the last video we said, hey, if we dotted these together, that's kind of the shadow component, and it's a scalar. It does not indicate that this is the vector. That's the misconception. But it tells you, you know what I mean? If you dot unit vectors together, it's a multiplication of 1 times 1, and then the cosine component. Well, it's the cosine of the angle between them. So here's the angle between them. Sun is shining on the sine. This is the sine component. This is the cosine component. So if you dot 2 unit vectors together, and you get a number that's less than 1, I mean, yeah, if these vectors are going in the same direction, you'll do the dot product and you will get 1. They're both going in the same direction. You know what I mean? It would be the same thing as having I, j, k. It would be if you had 2 vectors in the I direction, I hat dot I hat, well, you're just multiplying those, and then booyah. 1 times 1, you get 1. Cool. So how do we use the cross product to actually get this distance? Because if we cross this vector into this vector, we get a perpendicular vector. You know what I mean? You're going to do the right hand rule. This crossed into that we actually get a vector going in the other direction. But because these are unit vectors, a couple things are going to happen. One, this vector is going to sure have a direction, and it's going to have an I component, a j component, and a k component. Cool. But we can then, from that vector, take the magnitude. You know what I mean? That's just those components squared. And that magnitude is, well, it can either be a few things. It can be 1. That means that there's a 90 degree, these are 90 degrees apart. It's not 90 degrees. It ain't going to be 1. It could be 0. That means that, after doing the cross product, that means that these vectors are in the same direction. Because, you can't put your right-hand rule into one vector, and then if there's nothing to cross, if you're just going in the same direction, there is no leverage of those, vectors. So that would be 0. All right, hell yeah. So you're going to get a decimal, and that decimal, guess what that decimal is? That decimal is this component. Just as the dot product, you would get a scalar that's less than 1. Dotting 2 unit vectors together, you'll either get 0, 0, 1, or less than 1. And if you get any of those, that means that is that component. Okay, so after we do the cross product, we're going to get that vector, and then we're going to take we're going to get that vector, take the magnitude of it, and that magnitude is, because they're unit vectors, is going to be that percentage or that fraction of that. And then all we have to do is just take this 12 and then multiply it by that percent, because this is the hypotenuse. And so let's do it. So we're going to take this crossed with that. So we're going to take the unit vector a to o crossed with the unit vector a to b. Cool. And we're going to have k. K can cross in, and then this is how I do the unit vectors. I always draw, I think this is probably the easiest. Do the ijk, and then just, try it out. Put your fingers in I, roll them into k. Hey, that's a positive k. So I cross j is positive k. J cross k is positive I. And then k cross I is positive j. The other thing that I like to write is I just write this. I do I, j, k, and then I, j, k. Going this way, crossing this way is going to be positive. If I go the other way, it's going to be negative. I do it twice because, it kind of overlaps. So k cross I is positive j. You know what I mean? But if I go I cross k, that's going to give me negative j. All right, booyah. So let's do this. So we have negative k. I can cross it in with this term. So I'm going to have negative 1. I'm going to just multiply doing the cross product is still a multiplication. So never forget that. And then we're saying k cross I. So over here it'd be k cross I. Hey, we're going the right way. That's going to be a positive j. All right, next term. I can do k cross j. So I'm just going to do plus and then minus 1 for this term. I'm going to multiply it by 0.688. And k cross j. Well, looks like that's going in the negative direction. I'm going to do another negative 1. I do them in parentheses so I don't forget about them. And then k cross j is I. Sweet. So I have 2 components. That's cool. And so we're going to get negative 0.228 j hat. And then plus 0.688 I hat. So those are the 2 components. So now we have to take the magnitude of them. So in my calculator, this is just alpha j. No, never mind. No, this was alpha I in my calculator. And then this was alpha j. Sorry about that. So cool. So to get the magnitude, we're going to square these 2 terms and then take the square root. So we're going to take the square root, and maybe I'll just write these out. So we have alpha I, alpha j. Cool. So I'm going to take the square root of this term. Whoa. the square root of that term squared, so it doesn't matter if it's a negative. All right, plus the square of this term. So I'm going to take that term squared. And heck yeah, so this gives me that percentage that we were talking about, 0.725. So now I can just take the, and it's 72.5%. I can just take this and multiply by 12, and we got our answer. So I'm going to take 12 multiplied by that 0.725. And this horizontal distance is 8.705. So that's using the cross product from unit vectors, knowing that you're going to get a vector, but its magnitude is important. That's that percentage is this percentage. And then so we can multiply it by this 12 meters distance to get this perpendicular distance to this force. This is a right-hand rule, a distance to that force crossed in. If it's perpendicular, it's all juiced up. This distance times that 2, so times 2 gives us that 17.4 kilonewton meter moment. And we did this in the last video. They get this as a vector, but square root 16.5 squared plus 5.51 squared. Hell yeah, that's going to be 17.4. And so that's the magnitude that we're getting, 17.4 kilonewtons. So anyway, just kind of an interesting thing. Definitely not an easy thing, but it's good to go over mentally so you kind of understand how the magnitude of a cross product is related to that distance. Just as the scalar component of a dot product. Alright, sorry about that. Kind of just ran out of juice. But heck yeah, so the dot product, you know, that component can represent something. And if you get down to unit vectors, it's a little bit more maybe obvious of what that represents. I mean, if you get down to unit vectors, that literally represents that cosine component. And heck yeah. And it's not a vector, but it can be useful to describing the components. So that's how you can take a vector in any direction and then do the dot product in all the Cartesian directions. You get scalars. It seems like you get vectors. It still is just a scalar, but it is the magnitude. It's the scalar magnitude of a vector in that direction. So that's kind of cool. But it's only useful if you know, at least one of these has to be a unit vector. So keep that in mind. Because we could have done the same thing here, kept this as 12, and then just made sure this was a unit vector. But I just think it's useful to have them both be unit vectors, because then you just slice out that cosine component when doing the dot product, and we showed how to slice out that sine component doing the cross product. So alright, so sweet. That was cool. Thanks for joining me on this one, and guess what? That's a video.